All right. Well, my name is Andrew Monshine. I'm the Associate Dean of Research for the School of Architecture, and it's great to have the privilege to introduce our next panel, which is the Material Revolution, Pioneering New Approaches to Circular Construction. And this panel reflects on the social, political, and ecological consequences of material waste in construction and destruction from the American South to the global South. The panel draws from historic agricultural practices and emerging technologies, biomaterial applications, design computation, and robotic manufacturing to reconsider these methods in the development of a circular construction economy. And I'm excited for this panel, and especially excited to welcome our guest for the event, Professor Hanif Kara, OBE, and the design director and co-founder of ACT 2. We're very privileged to have you here, so welcome.
Thank you. Thank you, Dean, the president, and Thomas, my friend, for having me here, but Katie more than anyone. She was the one that invited me here without me knowing how many people I actually know here. So it's, it's really an honor to be here. When I tried to discuss with Katie what I would talk about, it kind of became very clear to me there were a lot of people from all over the world that are thinking about the same thing. And what is distinct about all of us is probably one of our problems, as well as the main engine for what will solve the climate problem. So I thought the best way to do this was really be contradictory in my own title for the lecture, is how to bind those distinctions. Why are materials particularly important right now? Most of the scientists and designers believe that in around 2022, we got to a stage where the anthropogenic mass increased or tipped over what nature has provided us. On the one hand, that's very alarming, but on the other hand, it's also opportunity. It means that we have made so much more material than what nature gave us in terms of what we can use. There's an opportunity not to throw all that away. So it's become a new bank for the next century or two. That's why it's important. The other very critical point, and I picked some of it up in your conversations this morning, is I'm going to speak in an era of deglobalization and degrowth. As an engineer, that's what I am, a structural engineer. So I'm faced with two front lines, and listening to all of you, I could even sense already that one of the problems of deglobalization is we're becoming too local again. So you were all talking about bits of land around you. Sadly, people like me are not in that advantageous position. We have to see the world from London, who caused many of your problems and many of everybody's problems. So we have to see from that world what the global South and global North is doing at the same time. This is very important because the diagram to the left is showing you that all new construction opportunities are in the global South. This has been going on since year 2000, and now it's actually gone over peak. Just right now, Saudi Arabia in the next 10 years, in one region called NEOM, will build 35 New Yorks. And once a week, the world is building a New York somewhere. On the right is the opportunity for the rest of the world, and I think you are slightly behind Europe because you're a younger country, the retrofit opportunities. So faced with these two front lines in the climate problem, I think that I have to step back and maybe contradict some of the things that were said earlier, but that's not intentional, it's just the way things are. My lens is that I'm sitting in that triangle as a design engineer, architect is to my left, and the rest of the world to my right. The wonderful place to be, because the architects are trying to travel to the right, especially the bad architects. They all want to be engineers, engineers, or something else. And then there are lots of engineers who are trying to travel to the left to be architects so they can wear black. You see, I'm not wearing black. So this lens is very, very important, and that's what I started to practice on 26 years ago this year. Why it's important is that I think this is the way in which we should think about in academy, because I teach also, to try and bind it together. Because if academy can get it right, both the engineers and the rest of the design people, we might have a better chance. The big thing that I want to talk about today is the changing importance of embodied energy, specifically as a structural engineer, because that has come to the fore in the last 5 years. In particular, operation energy is something we all understand and how it's contributing. But what's become very important recently is, when you see from the 1970 to 2050, the idea of what embodied energy from that first slide I showed you, how we can control that will contribute to the zero target on carbon. And when we know that buildings contribute 28% of that problem, we have a good chance of making a difference. The problem is we don't know what success looks like. Wherever you go in the world, all of these things, there are just too many international ways of thinking about success. Essentially, if the architects can get it right again, like they did 4,000 years ago, they could spell it out for the rest of the world, in my opinion. The other part that I'm going to show you very quickly is that I sit in that bridge between scientific research and design research. So whilst I'm a technically good engineer, I also understand design research. Both Brett and Gina talked about collaboration in a positive way. I am pretty negative about it. I think it tends to homogenize the best work we do. It's no disrespect to what they were saying. I think you have to be far more clearer about what you are and how you're looking at your work from your eyes, but also you're looking at the work of the other person. And that makes me sit in that bridge watching the scientists say we should ignore designers because we have all the funding and we'll do the research. And then the architectural designers who produce research for no purpose whatsoever quite often, and it ends up nowhere. I'm fortunate enough that I started thinking like this a while back. The situation we're in the UK is very clear now. We can either build nothing, which is the top of the curve, build less, build clever, or build efficiently. This is the Mayor of London's diagram, not mine, built by a number of experts, including myself. This is the kind of moratorium that we've been putting by law on ourselves. What that's created, and I'm seeing it here as well, it's kind of demonized two very important materials, steel and concrete. It's demonized it to a point where we're saying we're transforming, but let's stop building, because there has to be a transitional moment when these two evil materials, and by the way, steel you cannot get rid of. We've made enough of it to redo and reuse often. Concrete has a demon in it, which is cement, and we need to think about how not to demonize it, because when I remind you of that slide of what's going on in the global south, you should know that they are not even thinking about concrete. It just gets poured everywhere all of the time. Nobody even questions the discussion. I was in a similar conference in Indonesia, which has 32 million people, only 10 days ago, and I was just watching concrete everywhere. And when I mentioned this, it was like, what are you talking about? What other material can do it? So one of the things is understanding what the problem is, which is the chemistry, and I'll go through that. And then already saying that we can make amends in the transition period. So what's happening with 100% ordinary Portland cement, which is the guilty party, even replacing it with some blast furnace, which is also not good because it comes from coal fire, it's becoming a little better and less evil, and we need to move this across to the other part of the world, not to go through the same problems that we did in the north. There are better solutions of earth-friendly concrete, and I'll show you a couple of examples already appearing on the scene. So to get to zero carbon, we're going to have to move from the left to the right before 2030. It's not going to happen, but we will get towards that journey. I'm not going to go through too much data because it'll probably gets a little scary, but there is a lot of carbon saved, 65%, if we just move from the left to the right in concrete. So we could begin to amend or heal the problem concrete has created. When it comes to steel, how steel is made is the key. At the moment, the reason it's not a good material is because we use coal to make steel. Well, you will probably know, and if you don't, you should. Sweden has just started making the first green steel. So if you use electric arc or direct reduction iron, there are ways of taking that steel, which is quite abundant, by the way, still in the core of the earth, and making it carbon neutral, at least, if not heading towards carbon savings. So in terms of demonizing these materials, I cannot accept that I will suddenly have to stop my career, because suddenly stop building means stop engineering. And I thought I'd show you a couple of examples of how you do things a little bit better. I can't imagine a future without towers, but that's one of the things that London is stopping at the moment, and many of us are fighting. When you go to the other part of the world, that's all people are building, because we're moving to cities. And I don't know how it's going in the US, but I can tell you in China, even Africa, and much of East Asia, towers are very, very important, and they're not going away. So I picked on a type to talk about on how to do it better and what are the tools we're using to do it. This is a project with Herzog de Meuron, a very quick slide on it. It's a rotunda, which we all know every city has one. It's just a case of whose is better. The better thing here was that Herzog de Meuron don't often do a project unless they employ the client. It's the other way around compared to the rest of the world. So they chose to do this project on the basis that they're surrounded in Canary Wharf by a sea of extrusions which were brought across by New York at some point 30 years ago, and we have a tall buildings district, very successful. So they put this circular piece on the corner, which is residential, and they say what might be an excellent rotunda, a differentiating one that changes in height as you go. I'll go very fast through this. And one that actually offers something back to the city through the plan, but one that people don't quite understand unless you start to explain that the tools allow us to do this. So what we're doing is changing every floor to create a different amount of green footings, but also changing the stability systems from one type, which is what you normally do, to changing different types up and down. So the tools are allowing this kind of very smart work, I would say. So what we tend to do then is actually in this particular one, around the spiral, every room is different. So it is the most unusual rotunda you can ever imagine. And the walking of the columns happens throughout the whole building. So why am I talking about it like that? Very simply, this building has a 60% more facade than any tall building you will see. Usually, that's the point at which the tall buildings are killed, because of the facade ratio to floor. When you do something as clever as this, like the architect has, most of the values that we measure, the metrics we're using in the last 100 years are beginning to shift. So clients are paying for something like this, highly expensive, but it will make the money back. But more than anything, it reinvents a high-rise rotunda type. Its design and construction provide, in my opinion, an exemplar that might be replicated in the global south. I know, as I speak, that there will be at least 50 of these copied in the near future. So it's a slightly better way of doing things. You don't have to like towers, but it's very pertinent for me to go straight across to another one, which is the exact opposite of this in Iraq, because that's where the difference between the two front lines is for me. Why would you put a tower in this region where everything is low level across the Tigris? The reason is very simple, that in some parts of the world, non-modernization is actually threatening ecology. So here, the idea was really for Zaha Hadid to be invited back to a country to try and heal and repair a society, which is going to take more than 100 years after the damage we've done to this part of the world. Why wouldn't they want a tower, and why wouldn't they want to make it interesting? So there's a very different situation compared to the last tower, but we have to operate in this situation because they are using concrete only in this construction. And how can we invent something new and more interesting with the tools we have? So what you're seeing is a shrunken tower because of security, a solid block, which when the targets hit, because they have these low-level rockets, it won't collapse. So we've made it very robust and resilient at the ground level. And as it goes up, it splits into something else, and it becomes not four-sided, But around every elevation, you can see something different, but you see it as something different. So it's completely transforming itself as it goes up with a very simple move of turning the walls as you go up, but also making them smaller, bringing in more light at the top. So in terms of the context of this, I think it swings the pendulum where the high-rise is a generative force for societal pride, for some of the things you were all talking about, mending society beyond technology and construction. So climate is a secondary problem to actually making those people come back to the city. It should finish in the very near future. We're struggling to make it. It's taken time. The second thing I want to talk about is taking the high road on climate or the low road, because steel is worth just mentioning, as I started with how you demonize these things a little less. And this diagram basically, again, in Europe is now being worked to where the bottom, where the red is taking the low road of building new, and the top is when you take the high road of not building at all. It's called retrofit, which means absolutely nothing. It's one of those collaborative terms. You could retrofit a shoe or anything, and it doesn't really matter. But the point is, it's been hung on to as a mechanism to try and create a new architect, because those that are coming out of schools have never done retrofit. So suddenly the engineers are becoming architects and saying, well, we know how to do retrofit. This is what's going on, just so you're aware. My own position on this from the practice point of view is we're rebranding it as accelerated reverse engineering, because what we're saying is many techniques that you can use in order to look at an existing building and the different things you can do. For example, there are two very quick ones. To the left is how we found this tower. We did some work, and we discovered that from the 60s, concrete has increased strength. We also discovered, I think you mentioned, Jeannie, the codes. We discovered from the 1960s to 2000, there is a redundancy in the codes that's about 40%. So we were able to add at least 14 stories on top of this. We actually finished with 12 stories on top of a 21-story building. So you can just add without very, very much difficulty through a shift in technology. I'm going to try to go to one more, but I missed it there. There is another one of those which has just broken the record. We've put 22 stories on top of 4, and that's just won the Supreme Engineering Prize in the UK. But the one I wanted to talk about is a 1980s classic building. This is the other tower. So you can see to the left, it's very short, and that's what we've ended up with to the right, which has been awarded a lot of awards recently. I want to show you this one because it's a 1980s construction done by a very famous architect in a very important district called Broadgate in London, where we have taken steel to another level by taking an old box type of building, which was built in the 80-82 roughly. We've taken the old building and actually added things to it, but that's not all. So on the one hand, Michael Hopkins, the architect, has gone from a box to a blob by adding all this greenery, a beautiful atrium inside it. And we as structural engineers, despite the complexity of European cities under the ground, have managed to do this kind of work where we've transformed the building, taken the existing steel, which is the one on the left here, retained frame, and added only external frame and floors to the edges of it. Why do I tell you that? It might sound boring and technical, but the amazing thing about that has been that we've increased the net area of the building by 44%. So you can imagine how happy the client is because he can rent that much more land. But even better than that, all the steel that we did take off from there has moved. For those who don't understand what 44% means, how much carbon that saves, it's in the order of 120 cars driven for 25 years or food for 80 people for 65 years. That's how much carbon we managed to save by not breaking the building, doing a surgical insertion, and this is it finished. But why I mention it is because when you do something like that, the clients are willing to fund research. And I told you, I sit in this bridge where we fund our own research through projects. So this particular client, after winning an award for zero carbon, on net zero carbon on the building I just showed you, has just given us some money on another site to do the first cement-free piling. So concrete is not all bad. We're beginning to find materials where we can either use zero cement in certain situations or change the nature of the chemistry. Some of the steel from that building that we dismantled has been what is now being called urban mined. We've taken that steel, he has sold it to a friend of his, and we have added it on top of another building. So that steel is being reused, not just going to the scrapyard. Urban mining is becoming a big, big deal, particularly in south of France and Belgium, and I'll come back to it. This kind of thinking of advancing the reverse engineering also goes back to conservation and preservation. John Nash, one of our greatest architects, this is an iconic Regent Street building, which we were approached to look at very quickly. And it's grade 1 listed, so you can't knock it down or touch the external frame. But what we discovered through our tools was that during the war, at some point, it had been hit by a bomb and somebody had just reassembled a facade. So it was a non-John Nash building when we got there. Despite the fact that the city not knowing that, our tools were able to tell us that actually you could dismantle quite a lot of the old facade, which was post-war, and remake the whole of the John Nash original. And we've done it without any joints in the bricks, so using lime mortar, which is an old technique and very sustainable, bringing back a climate-friendly masonry system, which used to be around, so you can now recycle the bricks. And you can see some of the tools that we need forensically in order to make something like that work. Within the conservation world, I think there is a non-modernization problem generally, in that many parts of the world don't want to modernize because they think it's a good thing to do. I want to show you very quickly this slide because the Yemen cities, which are thousands of years old, 8 to 12 floors of mud towers we used as a tool with Foster and Partners to go back and look at how they've survived, not structurally, but environmentally. This is in Yemen, just north of the UAE. And we used old ways of doing things and said to ourselves, how would we put that back into a zero-carbon city, which is called Mazda in UAE? You probably all know, many universities were involved, that it was partly built. You can see it there. But everything we learned from the old, using new tools, made us capable of designing this with passive systems, including the materials we've used, to a point where in our street, the temperature difference is about 4 to 5 degrees C compared to a site next door. So just rethinking the urban form and making this passive ventilation as well as making better streets, we brought the temperature down in the street by 4 degrees. When you think we're trying to work towards a 1.5 increase at the moment, that's a result as far as I'm concerned. So when you want to modernize, you can go back to some ideas and not be afraid. And what this does, I think, is it helps us as engineers also have an ambition to change our own discipline. So most of the work you're now seeing, we are doing with our own tools in-house. So very quick, when the young engineers are starting, they have to make some very quick decisions on how to do something that's low carbon. And the only way you can do it is not through code. You have to go back to the basics and try and understand how you can measure the potential embodied carbon and therefore the life cycle assessment. So tools have an enormous capacity, provided they're driven by a non-collaborator, but a smart guy, a smart person, who can then collaborate in a slightly different way. So the future of concrete, the recent material, if you haven't heard about it, is called Ceratec, which was invented at Imperial College, and it replaces the limestone cement. We are just about to scale it up. It was invented by 2 young PhD students who came to us and said, this is a bottle of something we've got. What can we do with it? We've all gone through several rounds, and now the patent is being applied for. Last semester in our office, we actually made bricks out of Ceratec concrete and normal concrete and blast furnace concrete to look at the different strengths at a smaller scale. and we invited architects and everybody else to come and witness this. These people have just won the Nobel Prize for innovation. So major innovation is going on. It's more than just changing your concrete trucks to electric, which is what the cement industry is doing. You know, they're saving money saying, we can go to zero carbon by not using fuel when we drive millions of trucks to your sites. The benefit of this one is going to be quite remarkable if we manage to scale it up. So it's a low carbon concrete. Definitely it captures also the carbon from the atmosphere because of the chemistry that's been changed. Why do I mention concrete? Because I keep going back to what we're using throughout the world, but also some of the Pritzker Prize winning type of buildings. And when I look at them, most of them, this won a Sterling Prize for Grafton, I think that concrete is never going to go away. And this way of thinking should not be abandoned, you know, the basic idea of how you make a building. When they invented this building, the client was already nervous about, it's at Kingston University, nervous about using concrete. But what we were able to show them was, you know, combining these three boxes. It's a house for the city and the university. It's a fantastic building by Grafton. We could peel it all the way back to the most basic, simple, optimized systems in structure, so we could use as little concrete as possible, but also the most efficient concrete, and increase the lifespan of the building from normally 60 years to beyond that. So sometimes simplicity is the power of actually understanding this. And you're not going to give that to somebody who can't do complex buildings. Somebody who does complex buildings can do the simple ones better than somebody who does simple buildings all day long. It's just the way it is, as I see it. So what has that done when we published that? The other missing point, I said to somebody earlier, I don't see any developers or constructors in here. I think that's a major problem for you and for us, for everyone. So construction people need to be brought on board. That contractor was so pleased with winning the awards. We are together now with Cambridge University and many others, developing a steel and concrete low carbon cassette system, just going through. So the research is being funded by a construction company who won't patent it. It's just that their ESG also has to respond to the climate problem if their shareholders are going to be happy. I haven't stopped at that. For low carbon materials last semester, we went to, the studio was in Luma, in Arles, in Marseille. The studio itself was Sustainable Commons, which was housing for Arles with Fashid Mousavi. And then I ran a separate seminar on low carbon materials. So what we wanted to look at really was this dream and protesting that's going on about using straw and stone and timber. How far can we push it? And we started to do this work. We're just beginning to do it. And what we're learning is there isn't enough material to do it like this. There isn't enough craft. And in fact, frugality of this type will often result in buildings that nobody wants to live in. So we have to go as designers a step further and find a way of actually doing this better. And these students actually came up with amazing outcomes by the end of the semester. I got them to really feel what embodied energy is like. You know, what does it actually mean to get a material that's natural and then make something out of it, as you can see. The blind spots are extreme design processes, and the extreme design processes can bring blind spots. I want to show you two before I shoot off. A cafe with Thomas Heatherwick in the south of England for selling chips and coffee. And Thomas Heatherwick was asked to do this. The client was smart, and they knew if it's a famous artist sculptor, the art will take people there, and then you will sell a lot of chips and coffee. And it was a very simple idea, metaphorically. Driftwood was what he found on the site, and how could we recreate that in steel? And we took a lot of time to take the shape, not really interrogate it, but take it. How could we just make that shape? Used a lot of really complex software. These are images from Gary's software, some of you will know. We spent so much time really trying to rationalize this thing and find simple, cheap ways of doing it, and eventually came out with a fantastic paper project, only to discover that we had a blind spot, because the only way you could make that steel was through that machine on the top left, which is about 180 years old. So to bend this steel, it's still going there. It's not 3D printed. It's not all these things that we all read about, how we can make almost anything and mass customize. The old-fashioned crafts are still working like that. And they could only bend a 6mm plate. So all the optimization that I showed you on the tools and in the computer was largely wasted, because if we'd started from there, we would have designed it very differently. So blind spots are important. Blind spots can also be dangerous for somebody like us who's coming to the US to say things and upset people. So when we do competitions, we find ourselves in this situation. Broad Art Museum in Michigan, which is now old, which Zaha did, we won the competition by not doing a curved building, because the general feeling our side of the Atlantic was that you don't like curves. So we thought we'd keep it straight, and we'd go to Detroit and look at the car industry and take metal from there and fold it. So we also thought we were being very smart materially. This metal could do the structure, the environment, the light, and everything else. What actually happened is that the system here didn't allow, let's just put it that way, it didn't allow us to do it in the most perfect way that we thought was possible by drawing in craft from the car industry. In fact, we ended up making it like you make your houses. And the facade in the end was really just a rain screen. It's very beautiful. So the blind spot from our side was thinking that the USA is ready for something interesting. It was a mistake, I think. It's been a very successful building. And I keep going if I can. Have I run out of time? No, can I keep going? Okay, Serpentine Pavilion. So it's not all about natural materials. Sometimes we have to find materials from other industries that we could use structurally. So the Serpentine material, Serpentine Pavilion, is a competition usually. The last time that the creator of it, Julia Peyton-Jones, before she left, she created a competition and invited a number of architects. BIG were one of them. And one of the benefits was they had New York office, Copenhagen, we were in London. So one of the things about the Serpentine Pavilion is they choose a winner, and then you have 8 weeks to think, make, build, design, everything, and get it on site, 8 weeks. So you need the 24-hour clock. You also need strategies like this, where you produce 16 ideas, because that wipes out the competition, because one of them will have one of those somewhere. You then fire some of them and make sure that one of yours is going to succeed, which one. And then you invent a process. So the conceptual idea that Bjarke Ingels' group had was to make a brick, because that's what London's known for, but make it out of an advanced composite plastic that's recyclable, like the Formula One car, because it could be quite big, and it then had to be very thin to be affordable. To do that, you have to invent these complex nonlinear processes, which our tools can do, some of the things I've shown you. So one of the things I want to leave behind is really, when do you do this as an architect and pretend to still be an architect? Like, I do not do computer science or programming of software. I ask the computer engineer to do it, because they are so good at their work, they just don't know what the question was, often. So when you put the questions to them, what happens is they invent through their brain, which is not collaboration, what they want to do with the question I put to them. And then a question comes back in reverse, and it starts to create a new and forward-thinking frontier, in my view, at least technologically, which you could claim to be innovative. So these tools and integrated workflow are practiced at depth when you have to do it. When you're in a problem, like the climate problem, humanity has a potential to be able to solve some of these things. And here we developed a scheme that could not only analyze the whole brick system, every brick is different. It could do the formal calculation of how it behaves as an arch and so on, but it was measuring at the same time the singular brick. But we didn't have the material, we only had it as a sheet. So in parallel, we were making the material in Copenhagen, as you can see bottom right, that's the size of the brick, roughly the size of a coffin for some reason. But they were making those while we were analyzing to see if we can thin it down, because the thinner you can get it, the more likely it will happen. And then in parallel, going away from code again, none of these things happened through code. We had to test our assumptions and analysis based on physical tests. So you can see that as this is happening in parallel, we found really good correlation, and we were able to actually do the three things at the same time, which was imagine the form and the brick, analyze it, and make it and produce it all in parallel. So the whole of the linear process of construction is collapsed. And you need the construction people with you when you do something like this, because you can see that each brick has to be handmade almost, because they're changing in size, thickness, and where they are in the wall. So I wanted to just show you that a little bit more, because the other strategy is that most of these people don't like you to publicize it. So we did a drone video for ourselves, and on the day it was released, because the client often wants to take all the credit for these things. What we did is took a video without telling them and made sure that the world knew who the engineer and architects were. So there are other strategies that happen. This is a project with Thomas. We entered the competition together in Houston. I wanted to put it in for tooling purposes to show what we've been doing with it. Fashid Musavi is the architect with DLR. The three of us entered the competition together and beat some really good competitors. It's the Ismaili Center, which is a cultural center in Houston, has a prayer space in the ground, underground, but also some civic space up in the air, gardens, and beautiful landscape, 11 acres, right, with a small building inside it. So I just wanted to show it to you because I think it's, in a way, I'm hoping that it will bring the East to the US, because it's an Islamic, in theory, in Aga Khan. Aga Khan is an Islamic community idea that is not just stealing something and just applying it as a collage. It's been thought through, the landscape and the water features and all the other studies and research that he has done for the last 20 years or whatever. And then she's from Iran, so there's a little bit of Iranian Americanism in her, so you can kind of see the combination of the different people from different parts of the world coming into a wonderful city like Houston, which is ready, by the way, unlike Michigan. So they gave us a lot of opportunity, and I'm showing you very quickly where we are with it at this point. Bioclimatic tools is why I brought it to this table for today's discussion, because as well as analysis, we are beginning to enter how do you refine wind? What is the effect of wind on the climate, on society and people, not just the other way? How does our building stand up in wind? We're also looking at air quality analysis at the same time. So this is structural engineers. We're having to do this very early. And in locating this building, we did a separate piece of research at our own expense recently to see and make sure that all the intuitive tools were actually confirming what we were doing. And today, I think we're at a stage where we picked it at exactly the right place. Sadly, it's got a lot of concrete in it, and we're struggling with the quality of finish because it's pulverized fuel ash. And it's just, this is, I think, video taken last week. Some amazing structural ideas, but I'm not here to tell you about what a wonderful engineer I am. So, extreme environments, this is a project that Katie did when she was at GSD. I was with the office of OFIS. I always collaborate when I teach studio, because I don't believe an engineer should be an architect, ever, and the school doesn't like it, but I always collaborate with different architects. So in this case, it was office, and the project was really for the students to design something, a retreat up on the top of a mountain, which we built. I'm not going to go through the detail, but it triggered something else, which was the understanding of mass timber, because even though we were beginning to use it, we had some ideas on that student project. We had done the first house in the UK using this image. Is a postcard image of a protected area, And the architect had decided, because the conservation wouldn't let him build anything, he would build the shadow of the building as the extension to the building. So what you see in the background, the black, you never see that. So it's got to be removable because it's a conservation building. So we built this thing in mass timber, which is a slightly different way of designing compared to what we do with the normal timber systems. And it pushed us to go further. And with one of my colleagues, Jennifer Bonner at GSD again, she had bought some land and decided to do this in Atlanta, which we managed to do a very successful project called House Gables. Again, we went through a nightmare in terms of procurement. Nobody wanted to build it. It was 40% cheaper to put it in a container from Austria and assemble it here, believe it or not. So this is how the supply chain of deglobalization is going to affect us. So I thought between the two of us, we were so frustrated by the system that we did a studio together at GSD, and we thought we would start to put some reality checks and invite more architects to get engaged in the material. Because like all new things, you are edited out. As soon as CLT was invented, some architects were saying, I'm the expert, you should come to me, like hospital architects will say, other architects can't do hospitals. The industry was saying you don't need an architect, it's a material that comes straight from the shop. So Jennifer and I had a challenge where we thought we'll get a Scandinavian contractor to sponsor us and look at the way in which we might use mass timber and architecture it through using art and architecture. You think of it as a space. And we did a very successful studio in Raleigh, actually, not far from here. And we compared housing systems with tall buildings. And it got published, a very successful book. It's kind of, in my opinion, allowed many other architects access to CLT instead of being afraid of it. And clients love it. Why I like it is because we suddenly were thought of as the experts. And we have built this with Thomas Heatherwick, which is a health building, a health facility, cancer research, all out of timber. Super successful, won a lot of awards. But more than that, the prize is the Google headquarters, which is 400 meters long. So that if you stand it on its head, it's taller than the Shard, with Bjarke Ingels, Thomas Heatherwick, a park on the roof, and the largest piece of CLT, 30,000 square meters. So there are places where you don't have to ask why CLT. In this case, the client wanted the ability to dismantle the floors, be able to open, in the middle diagram, some floors at certain times of the year, and stack the material. And the only material that can do that is CLT. Timber can't do it as easily. So it's currently the biggest timber floor in the world and almost finished. But the nice thing is there is a spoiler alert for fans of CLT. Okay, I got to finish. I'm told. So this is how much CLT you make. That little building, you need 6 hectares of forest to do it. I'm going to try and finish really quickly. I'm sorry I've gone on longer. It doesn't stop there. So Kundibari in Bangladesh, which is a $250 house with Marina Tabassum, the problem is that all the joints are steel, and we invited her to put it in Royal Academy and relook at 3D printed joints in more greener materials. I'm going to skip these now and get to the end, if you don't mind. I just put one in Africa, just because we met last night. So in Ethiopia, we've been looking at how to go back and be really local with their materials and make facades. And this is art entering the scene. Olafsen took us there to make facades out there. I'm going to conclude, but I have to show you this video. I have to show you this video because it brings bamboo, mud, and everything together in Milan, which is where you buy expensive suits normally. But that's where this was done last year in Milan, where we were using drones to spray mud. I'm finished, but 2 final slides. The takeaway for today, the 3 axes, the value, which I said to you is changing from a statue to a dance. Complexity is being driven by AI now, so everything can be done. Almost everything, you can ask the question. Efficiency and planetary boundaries are driven now by climate. So that cube that you see is the area of compromise that I'm operating in. I think it's a fantastic thing, and if I was much younger, I can imagine the practice being even bigger in the future. One final thing about the hegemony of technology and science, it's binary, it has no soul. As Marshall McLuhan said, it's not innocent. You can do things with it to tell lies. You can remove the need for agency and accountability, and pervasive analytics, like I've shown you, could be very convincing. All of this wouldn't be possible without my office. There are 30 nationalities and 300 people doing all this work. Thank you. Sorry, I took long.
Thank you, Hani, for your presentation, and thank you for having me. And I'm very happy that Hani finished with the MOD project, because I'm going to talk about MOD. And if you don't know me, I am Ehsan Baharlu, Assistant Professor and Director of the Computational Tectonics Laboratory at the School of Architecture. I received my PhD in engineering from the Institute for Computational Design and Construction at the University of Stuttgart, and I have a postdoc at MIT. My research focuses on integrating material capacities and fabrication limitations into design processes. In this presentation, I will present my research on advancing mud tectonics with an approach to ecologically activate building envelope. In 1960, Seckler, in the paper Structure, Construction, Tectonics, highlighted the expressive qualities of the corresponding relationship between forces and building parts that can only be described through the terms tectonics. Tectonics is derived from the Greek term tekton, means builder and carpenter. To build or construct, we need to understand agencies involved in the design processes. One of the main agencies in is the material systems and their role as active drivers in the design process. The other one is fabrication techniques, such as industrial robotic arms, to consider fabrication possibilities and limitations in design processes through a computational design framework. This computational design approach can integrate these agencies in an expressive form to embrace the tectonic of form and structure. Computational tectonics is a computational design approach using advanced algorithms to link materialization processes with form and structural expressions. I'm happy that, Hanif, you cover all the material issues, so I make it very simple here. So the relationship between material and construction with environment can be considered as one of the main factors in changing the climate by emitting carbon. Research shows that the emission of carbon dioxide in the built environment is more than 50%. The carbon emission is 28% for building operations and almost 23% in production of building materials, such as concrete and steel. One approach to address these challenges is applying methods like cradle-to-cradle or a circular economy in building construction. A circular construction is an alternative for conventional method of linear construction that focuses on take, make, and dispose. In 3R approach, reduce, reuse, recycle, we have this opportunity to reduce the use of materials and as a result, the amount of carbon emission. This method aims to repurpose the recycled materials and reduce the use of raw materials and residual waste. A type of material that has enormous potential for building construction is natural or eco-friendly materials. According to the World Business Council for Sustainable Development, the use of bio-based or eco-friendly materials with the properties of carbon sequestration will reduce the carbon footprint of buildings. One of these natural materials that has been used in construction for thousands of years is soil. Mod 3 is an attempt to test the process of circularity to explore the tectonic potential of earthen materials in 3D printing non-standard forms that addresses the challenges such as buckling behaviors. With a sustainable approach, we use Virginia red clay. We pulverize it and grind it. After a series of tests of the mechanical sedimentation test, we prepare the dry mix, we make a wet mix, and after that, we just started to use robotic fabrication to 3D print this small artifact. We developed a computation framework to simulate the buckling behavior of them while generating a toolpath for 3D printing. The computation framework is a parametric tool that monitors the user's input to be the parametric spaces, to be inside the parametric space. In this image, in the left image shows the process of fabrication, that the layer of earth materials deposited on the specified location, and the right picture shows all artifacts standing next to each other. As I mentioned, in advancing mud tectonics, we tried different approaches to keep the earth structures ecologically active. We developed a mixture of mud without any chemicals and additives. This mixture is viscous enough to be 3D printed and has enough nutrition to support seed germination. We tested our ecologically approach on a mud tree project to prove that the developed tectonics can maintain its structural integrity while it's completely wet. And in the left image, seeds are mixed with the mud, and after a few days, in the right image, seed germinated. It is worth noting that this artifact keeps its water content to provide moisture for germination. It also maintains its structural integrity while the roots pass through the layers. Prior to the mud project, in collaboration with Professor Jima, Department of Material Science and Engineering, and Professor David Cott, Department of Environmental Sciences, we developed this ecologically active structure. Particularly in this project, we started to study about the feasibility of seed germination while measuring the water content of the soil. And we tried to move toward more architectural elements, such as dome-like object. Here you can see the process of 3D printing with a robot and with a simple extruder as a putter bot that extrude mud on the location while we are sprinkling seeds on it. We kept seeds to grow fully and to start seedling to cover the dome structure without damaging it. We continued the tectonic exploration by parameterizing the forms, changing the radius and the height of the prototypes. It shows at which level the overhanging can work and when the deformation will occur according to the form. For example, in the images top, you probably can see that it cannot cover the whole dome, and it just started the buckling at the left image. We continue the tectonic, and an ecologically active structure, we call it, is a structure that maintains certain conditions for flora and fauna. We started to develop a mixture of mud without any additives to be printable and provide us with the possibility to scale up the process. We adjusted the fabrication process from the small extruder to use a progressive pump. The process of fabrication was aligned with the circular construction. We reduce, recycle, and reuse the soil until we achieve the desired tectonic system. This can be called a regenerative design process to rethink the mud architecture and revolutionize it. Here, you probably can see we targeted a building element, which was part of which was a partition wall fitted between the stud structures. One side of it was designed to germinate, and another side left to be considered for finishing layers. The space between these two surfaces is suitable for adding insulation and eco-friendly insulation, such as hempcrete. You probably can see here the back is not germinated, but hold the structure, and in front it just completely germinated. Here you can see the final installation between the stud structure. It shows the time lapses of growing seeds until it completely covers the outer surfaces. In conclusion, advancing mud tectonics manifested in this series of projects uses local resources and seed germination to not only be a suitable approach, but also sequestrate the emitted carbon to the environment. With an ecologically active strategy, we can move toward a carbon-negative future construction. I would like to thank my researchers who were involved in this project. the School of Architecture Fab Lab team, Department of Architecture, and Dean's Office. Thank you.
Is this the clicker? Great. Hello, everybody. My name is Mohammed Ismail. I also go by Mo. It's a pleasure to be here. It's an honor to speak, especially since I just started teaching, so I have very little to show for my time here. But interestingly enough, a lot of what I'm going to talk about started with my MArch thesis when I was a student here, myself advised by Gina Ripple. And so it's an honor to kind of look at the full circularity of it. And just like with Ehsan, Hanif, you covered half of my slides, so I'm going to just speed through a lot of what I got here. But I want to start with this visualization. So you've heard the statistics. We're building the equivalent of a new Paris every week. Urbanization is beyond precedented rates at the moment. This is a map of urban growth over the next 80 years. And what you'll see very quickly is that most of this urban growth is happening in, clicking the wrong one, is happening in developing countries or less economically developed countries, the global south, whichever term you prefer. By 2050, 90% of urban growth is expected to happen just in Asia and Africa alone. What this means is that we need to build quite quickly. I also want to note that this is both an academic and personal interest of mine. I grew up abroad. My family is from kind of different parts of this. And so this is a reality that a lot of us see if you're with a similar background. And so for me, what that's meant is seeing things like this. This is a common sight. This is a photo from Khartoum, Sudan, which is where my family is from. And what you might see is a family that has most likely been allowed to squat in an unfinished construction site. So it's a concrete frame building, most likely residential. The family building it probably didn't have enough money to actually finish it, and so they allowed this family to squat in exchange for them watching over the building materials. And so it reflects this really interesting urgency and reality, which is hard to kind of connect with what we see here, which is essentially that the equations for the cost of construction are not the same everywhere. As opposed to, say, in a more economically developed country like the US, where labor really drives a lot of our choices, and so we can kind of get away with less efficient structural systems. We don't care so much about how much we're doing. Less economically developed countries can have materials account for more than 80% of their construction costs. Now, Hanif spoke a lot about concrete, so I'm just going to drop a few extra statistics on top of everything he already said. Since the Industrial Revolution, concrete has outpaced the use of every other material. In fact, by today, we're producing 2 times as much concrete as all of our industrial materials combined. It's second to water as our most common material. Now, why is that the case? Part of the demonization of concrete is that it's just really good at what it does. We don't really have many materials that are as affordable, as available, fire-resistant, durable, but most importantly, in my opinion, is that it's trusted. We've used it for over 100 years, haven't changed it very much, and our building codes are quite hard to change, if anybody is aware of this. And then when we look at where this concrete is being used, currently China is outpacing the rest of the world, but places like India, Africa, by 2050 are expected to explode in their use of concrete construction. And this is largely because of those urbanization statistics. And what's interesting is if we look at our carbon emissions globally, we say about 11% is just due to construction. In developing countries, it's 2 or 3 times as much. The carbon emissions associated for that country is associated with construction. So it's even more important for them to start considering these systems. Residential construction uses about half of our concrete around the world. It's more in LEDCs. Basically, every statistic I say is exaggerated when you look at a developing country. And most of these systems use what we call flat prismatic concrete construction. Everything is kind of rectangular. It's a system that is developed primarily to reduce the cost of labor. And so it doesn't really necessarily make sense for us to use the systems developed in places like the United States and the UK in a place where material costs are not the same. And horizontal spanning systems, which is just a fancy phrase for floors and roofs, constitute most of that material. This is a long explanation to talk about why basically everything I'm going to show from here on is just fancy floor systems, because floors are really where you can make the most change immediately. They can constitute about 50 to 80% of structure's carbon and mass. We've known this since Galileo Galilei, since the 1600s when he developed what we call the elastic theory and beam theory. He realized that you could shape a beam according to the amount of force in it. It doesn't have to be prismatic, it doesn't have to be regular. And we know this because of equations and diagrams like this that tend to make architects very uncomfortable. But this is a shear and moment diagram for a beam that's simply supported holding a uniform load. We know that the load is not the same everywhere. There's a different amount of material that's needed to accomplish what we call uniform strength. And so that led to a hypothesis in my research, which is that through geometric complexity, we have an opportunity for material efficiency. This requires a lot of different types of things to come together in order to develop a solution like what I had just shown. But basically, the idea is that we don't necessarily have to build the most efficient system possible, but we might be able to achieve something that is more efficient than what we're currently doing. And we can do that according to the constraints and the opportunities in each context. And so I developed a shape optimization method that required going through building codes and coming up with ways to very quickly come up with how much steel there is in a concrete element, where that steel is located, how much it deflects, how much steel do we need in order to make sure this is still considered a reinforced concrete structure. All these things have to happen immediately if we want for optimization to occur. These are equations that tend to take 10 to 15 minutes for a well-trained engineer to actually figure out by hand. But what's great is now we can actually automate this, build it into a tool that looks like this, and then run something we call constraint optimization, where we have some kind of design vector controlling geometry. We're trying to minimize some kind of cost that might be embodied carbon. It could be monetary costs if you have those numbers. These are all numbers that change according to context. But the method is flexible enough to account for those changes in context. And then it's subject to whatever constraints are necessary, depending on the building code, depending on the practices that are available in that region. And this is what that optimization looks like. It's a little more interesting when it's animated. But it's basically running hundreds of those calculations that I just showed in the slides before, but automatically. And it's doing it iteratively until it reaches a solution that is both more efficient and safe and reaches all of the code requirements necessary. This is another image of some of the tools that we had developed in order to do this. It can happen at element scale. It can happen at the system scale. You could look at a full building at the same time. But that's all possible using this flexible methodology. Now, what's slightly complicated about this, and in my interest in making this an actual accessible method, along with everything else, is that there's a lot of decisions that go into building design before this even comes up, before you're even looking at your concrete floors. And so you need to be able to actually account for those through early stage design in order to account for, to allow for scalability. That means decisions like how big are the floor loads, how far are columns apart. These are all things that you might be changing up till the very last date. And it makes it really hard to run a 40-minute optimization every time you have a new design layout or a new floor plan. But what's exciting about that is we have new tools, we have new methods that include things like machine learning and AI that we can borrow, surrogate modeling, where you can take all of the past data that you've collected in the past and actually start to iterate and predict solutions in real time. And this is what this neural network architecture, for instance, does, where it takes some of those design inputs that an architect might still be playing around with and then turns it into a geometry and turns it into a predictive performance, which means that you can actually get real-time response where you can play around with your column spacing, your grids, see how much carbon and mass there is per unit floor area, and then compare it between a flat slab and a shaped slab. And this doesn't just have to be for regular floor systems. This is an existing a weird pavilion design between a curved plate and a slightly wonky wall. And it still gives you that same production, how much embodied carbon you can reduce, while knowing that those designs are most likely very close to structurally efficient and safe. And this is another one where we can start to enable workflows that already exist, like virtual reality tools in Fallogram. I just use an iPad, I point it at the room, and I mess around with those same inputs, and it gives you a predicted performance according to the design inputs. And it doesn't have to be someone who's necessarily trained in architecture or engineering. This is something that you could bring to a potential client or someone who is looking at affordable housing options and doesn't really know what it's going to look like when we're considering all these options months ahead of time. Now, none of this really matters if we're not able to build it, obviously. Everything I've shown has been a really nice image or video on screen. Luckily, I've had the opportunity over the last few years to work with a number of really amazing local partners who understand construction. And so it was a back and forth between them. For instance, we developed a prototype in India that was 50% less embodied energy than the standard floor system. And this was the first full-scale prototype, and there are two main lessons from this: that we could design things that were efficient and that we could design them according to what was available. For instance, we went in with this assumption that you could do CNC milled foam, found out that foam was not available in the quantities that we wanted. But just by simply adjusting the parameters and how they're related to the final geometry, we could redesign a floor system that could be built using steel form, laser cut with laser cutters that were already available in Delhi and welded by people who already have years of experience welding steel. And so I didn't have to do anything in the fabrication. We had these amazing people just pull this off in a week and then build a form, test it, and prove that this met the design codes accordingly in India. It had the predicted behavior, failed in a ductile manner. These are all fun engineering terms, but basically it was safe and it met the requirements. We also worked with colleagues in Arkansas to design a very similar system, and this was brought about by some research they had been doing, where they had developed this awesome system called ZipForm that allowed them to build complicated 3D forms using simple welded plate steel. So it's just something that could be cut out flat, and then it was forced together through a jig. This is my colleague Emily Baker doing this with students who had never worked with steel before, and they were able to figure this out themselves. We're embodying the complexity of fabrication in the design process itself, and that way there's no guessing when you get to the actual construction site. It just comes together like a puzzle piece. And again, awesome testing lab in Arkansas where they proved that this met the structural codes that we designed it for. This is the last prototype that I'm going to talk about. It was my favorite. We worked with amazing partners in Mexico to develop a block and beam system. This came about from a conversation with affordable housing constructors who'd been using the system since the 80s, and they had never changed it. And so we asked if we could design something that was 50% less carbon intensive, less material intensive, and we had the opportunity to actually build a prototype as a pavilion on behalf of MIT. This meant that we had more resources than usual, so we got to actually propose something that was maybe a little less realistic, but more efficient. And so we worked with this amazing fabricator in Mexico City who started her own 3D printing workshop, or robotics fabrication workshop, to 3D print these tiles where every single one of those blocks are different, but the cost of them is exactly the same. And they're all using local clay. They can be broken down and recycled, and then it could be fabricated on site. And so we brought together a number of contractors. Again, it was almost automatic once we had designed this according to what they were able to do and what they knew. And then built this pavilion that was visited by thousands of residents over 2 weeks, which was amazing. We never got to actually load test it, which is a shame, but this little girl did some lateral load tests on our behalf. It also survived 2 earthquakes, which was great and a little scary, but it did make it through that. And so I just want to end with a couple of really quick thoughts. This is the only slide with a lot of text on it, but I just want to bring back maybe some of the lessons that had come up this morning. There is definitely a clear inverse relationship between the regions that are responsible for climate change and those who are suffering most from it. And those who are suffering most from it happen to be places that are also urbanizing quickly. And so we need to figure out how we can have the most profound and immediate impact. Holistic design has to occur across various performance metrics. I talked mostly about structures, but I've worked with people who are working on thermal, energy storage, acoustic behavior. There's a lot of different things that we need to bring together in order to make this work. And sustainable building practices have to need to question our most basic understanding. It's not enough to build the way we've always built. And with that, I'm going to stop. Thank you so much.
Good afternoon. 3 hard acts to follow, but we'll close out the day. We are Katie McDonald and Kyle Schumann, and we're both assistant professors in the Department of Architecture. And today we'll discuss how our material-centric body of work responds to the built environment's contribution to global carbon emissions, which is approximately 20% from materials and construction alone. So we do this through two facets, one which we'll touch on briefly, and the other which is based at the University of Virginia. Together, we run the professional practice After Architecture, a studio named to convey the built environment's impact on cultures and ecologies. And this is, most of the time really a two-person endeavor through which we've completed permanent works ranging from a public memorial in Washington, D.C., to a private cabin in Vermont's scenic terrain. And here at the University of Virginia, as a complement to our professional practice, we co-direct an academic research lab, the Before Building Laboratory, which pioneers new material assemblies to advance circular construction. Maybe the biggest joy of that is working with a team of paid student research assistants to engage emerging technologies and invent new technologies which enable us to work with new natural materials in new ways, as well as develop carbon sequestering material assemblies. So we like to start our talks with thinking about how society has considered natural materials in the recent past. And so we'll talk about two ways to straighten a log. Understanding the embodied intelligence of natural materials is central to our approach. Let's begin by considering that since industrialization, the answer to how to straighten a log to transform its kind of raw or arcing form has been to subtract. And so it's subverting the kind of natural geometry of the log, which balances the search for light, water, and structure, and instead transforms it into a prism to break it into a uniform element, producing waste and consuming energy. So we find favorable an approach embodied by this piece by architect Alan Wexler, entitled Reframing Nature, in which instead of a subtractive approach, he takes an additive approach. Incisions are made into a wandering trunk, and wedges slip into the mass, redirecting the center line into a straight path. The additive operation maintains the trunk's taper, its protective skin, its efficient surface area. And so the next question we'll ask you is perhaps why is it necessary to even straighten or standardize the log in the first place, which informs our opportunistic approach to leveraging material qualities. Today we will present 3 tactics to harness material intelligence in construction.
So the first tactic is entangling. We're going to ask, how can we move from a model of purpose built to purpose grown? The first project, the parklet chair, is a collaboration between us and barley seeds that are grown hydroponically into shaped molds. Seeds are manipulated to shape the direction of the gravitropic roots and the heliotropic sprouts as these plants are germinated and begin their growth. The chair self-assembles through the interweaving of these growing roots, taking form as a landscape displaced from soil, water, and sun and resituated into the interior. Everything you see above the wood legs here is made of nothing but the grown barley. There are no glues or adhesives used in the production of this object. It's both real in that it's grown, but also unnatural in that it's cultivated indoors and without soil. This tactic of entangling is then scaled up through the construction of Homegrown, a project which defines an application for the poster child of invasive plant species, also known as the vine that ate the South, kudzu, which I'm sure many of you are familiar with. Homegrown expands the inventory of grown construction materials to species which are not cultivated and harvested, but instead removed from their environment as an act of remediation of the native habitat. The installation entangles discrete parts into 4 wall panels, which form an exterior room in this garden context. Read alternately as a rune or a topiary hedge, Homegrown repositions the aesthetics of a digital fabrication, replacing the smooth, crisp, machined tectonics that are synonymous with the digital turn and with mass customization, instead with an architecture that is fuzzy, fluffy, furry, and shaggy.
So the second tactic that we'll describe is bundling. We seek to develop applications for grass building components that marry the precision of industrialized tubes with the structural intelligence and flexibility of branching geometries. In this project, we are working with colleagues Merrick Pandera, Jose Gomez in engineering, and Deborah Lawrence in environmental science to analyze material capacities and to specify grass species which will optimize carbon sequestration and minimize environmental impact. The resulting system is piloted as a large-scale branching model, as well as a more regular, modular, full-scale structural system.
Our third tactic is twinning. Twinning refers to the creation of digital doppelgangers of physical artifacts through both 2D and 3D imaging technologies. So if we think about traditional project delivery, it typically involves the creation of design documents long before the material is ever acquired or sourced. Instead, we want to think about how twinning can leverage 3D imaging tools to inventory material inputs and allow the design process to progress as a dialogue between design intent and material agency. An example of this, our project Tangential Timber pilots an application for nonlinear wood. 48% of timber that's harvested or produced through forestry practices is deemed unfit for construction in its whole state, and is instead shredded down and composited with oftentimes toxic chemicals or burned for fuels. And so instead, we're looking at a different use for that material. Through this, we developed a custom low-cost, low-data workflow that documents these cross-sectional slices of logs called cookies in the timber industry. Cookies are photographed and traced in 2D and then translated into 3D digital twins. And we created a test assembly that consists of this compression-only vault structure with digital scripting tools used to sort these cookies, every single individual piece of material, across the form of this pavilion. The joinery is then tailored to fit the profiles of each cookie, so it's highly specific to the two pieces of material or two or more pieces of material that are coming together, and minimal part reduction is performed with a 5-axis water jet and a 3-axis CNC router. The timber units double as both structure and ornament. The structural stress lines inscribed on the surface of the vault register as almost a second wood grain overlaid with the grain of the cookies themselves. And these lines double as a graphic pattern for aligning the wood masonry units as you're assembling this giant 3D jigsaw puzzle. Another project, variable sawmilling. We're working with mechanical engineering and environmental science faculty, including Gavin Garner and Manuel Lardau. And we're currently developing tools that will allow us to mill logs based on their natural curvatures. So we tested this approach by taking low-resolution digital scans of a series of logs and mounting a commercial bandsaw to a robotic arm. And through this process, we're using 3D scans that are used to guide the saw's toolpath, making it possible to precisely mill non-linear and non-standard wood elements and open up applications for this global material stream. At the same time, robotic arm systems are expensive. They're amazing, as we know, with the new one we have at the Allied Space at the School of Architecture. But these arms are difficult to move. They have some limitations in range and have complex electrical and structural infrastructural requirements. So in order to think about this as a democratized technology, we're working on developing a low-cost mobile robotic sawmill that will allow for widespread access to this as a tool for working with nonlinear wood and hopefully be transferable to other cultural and ecological contexts globally. This research will soon be exhibited at Exhibit Columbus, a world-renowned architecture forum hosted biannually in Columbus, Indiana. This is a kind of a citywide museum. Columbus is home to 81 significant works of architecture, and for this year's exhibit cycle, entitled Public by Design, focuses are on community-based design and the challenges facing activating historic downtowns. So our team was one of 7 university design research fellow teams participating in this year's cycle. And our project asks, how can construction make use of waste? A primary source for the project, both figuratively and literally, is the former Irwin Block, a Queen Anne masterpiece, which is located just a block away from our project site, which was lost in a fire in December 2022. So working with the building's owners, we're engaging with this material and cultural memory of this important building. Specifically, we salvaged 2,500 bricks from the ruins to be reconstituted into our installation at the Columbus Area Visitor Center. The reclaimed bricks will be placed in dialogue with a second material system and one we're developing specifically for this project. Over the last 15 years or so, cross-laminated timber, or CLT, which you heard about from Hanif today, has emerged as a desirable kind of building product, particularly in the US, which we're following kind of on the tails of our European and other colleagues. And these massive structural panels are composited of stacked and glued layers of dimensional lumber. Instead, for Exhibit Columbus, we're looking at cutting nonlinear wood on our custom robotic sawmill and compositing it into curved and twisting and irregular panels that might utilize the natural curvature of the tree specimens and also increase or change the structural performance and the formal and architectural and spatial potentials of these structures. So together, the curving timber panels and the brick gabion build upon the planter wall that links the Columbus Visitors Center to the Cleo Rogers Memorial Library by IMPE. And timber panels are offering thresholds and overlooks and furniture, while the gabions form railings and other surfaces, creating a wooded oasis for reading, dining, and play for the community in Columbus, Indiana.
To make an impact, we need to work together, and I think that's fundamental to the attitude of this whole event. So we're really grateful to Dean Hudson for putting this on in the School of Architecture. We recently curated the Biomaterial Building Exposition at UVA to bring together scholars advancing a radical material future. Architects from 5 universities exhibited full-scale installations here on campus, while a gallery show framed a larger field. Also key to this dialogue are the voices of the next generation who will champion the climate future in practice. In our core coursework and teaching, students are advancing material research, and they're making an impact. So we hope to imagine and pilot a radical material future, and we hope you'll join us.
Thank you.
Thank you.